one was the modeling, which is manipulator modeling. Okay, by modeling we mean how does the kinematic behavior and the structure and the structure of the manipulator. Okay. Then we spoke about planning, which was path planning, right? And we also did velocity or the Jacobian. And we spoke about planning, which is your path planning. Okay. Let's go to a discussion about, finally, once you have planned the path, once you know how the manipulator moves, let's talk about control. Okay. Control strategies, that is how to control the motion of the controlling the motion of the manipulator. Okay. Now, when we speak about control, this is more related to EE, but anyways, since this is a very interdisciplinary course, we will go a little slowly and we will talk about control. Now, if you have a manipulator like this, and this is a 3 degree of freedom manipulator. Right? Each of the joints, you can move each of the joints by applying either a force or a torque, right? If you apply a force, that means this is a prismatic joint. So if it's a prismatic joint, you'll apply a force. Along what axis will you apply a force? What axis will you apply a force? A force along Zi minus 1, okay? Because the direction of motion, if you have a prismatic joint like this, the direction of motion is along Zi minus 1. Same way, if you have a revolute joint, this will be a torque about Zi. Now, torque is basically a force that will rotate the joint. So if you have a joint like this that you want to move, and this is a perpendicular axis, Zi minus 1, you'll apply a torque like this to move the joint however you like. All right. Now, if you study systems, normally what you have is, if you have one actuation mechanism, if you have a single joint like this, then you have a single system which is single input, single output, because you're only moving this by one direction or 1 degree of freedom. Now, in this case, you have 3 joints. So when you do a control loop, you control each of the joints simultaneously, because that will lead to the manipulator moving in some direction. Last time we did a trajectory generation. We devised a cubic trajectory, Q of t, which was a 3rd degree polynomial. Right? And this was for one joint. You do the same thing for Q2, Q3. So all the 3 joints will have a trajectory. So this will have a Q1 trajectory, this will have Q2, and this will have a joint trajectory, Q3. So that will lead, when I move along this trajectory over a timeline, let's say 1 second or 2 seconds, and my manipulator will move from here to, let's say, this point. Right? Eventually it will go there. Now I have to move all the 3 joints simultaneously from here to here. So this one will go from theta 1 to Q1 dash. this will go to Q2 dash, and this will go to Q3 dash. All in a span of delta t, so that we have all the three joints moving, so that the manipulator can move from, let's say, a point A to some point B in the workspace. Right. Now, we cannot have one torque that is applied to all three joints. Each of them will have their own set of torques or forces, T1, T2, and T2, right? And this will change by position to position. So in this case, when you control each of the joints separately like this, it's called this type of a architecture where you're controlling each of the joints like this. It's called a independent joint strategy. Okay, so we call this as independent joint control. Okay, so we call this architecture as independent joint control. Okay, so independent joint control is controlling each of the joints independently from each other. Okay, so all the joints are controlled based on their specific trajectories. Okay, based on their own joint trajectories, this is controlled. So this is controlled by Q1, this is controlled by Q2 based on how it is moving from there. Okay. Now when you talk about control, there are two methods. So whenever you do a controller loop, there are different architectures that we employ. So for example, if I want to move, let's say I want to move this table from here to there, right? So I'll apply a force. I don't know the weight of the table, right? If I ask you to move this table, you're not going to bring a scale and measure this and look at the dimensions. You will just move it. If you overshoot or if you go further, you'll pull it back, right? Or you'll just go on slowly moving till it reaches the point. So in this case, you don't know what the parameters of the table are. You're just going by your own visual interpretation or visual feedback. So in this case, if you employ a similar mechanism in the case of a joint control where you don't know the mass of the links or you don't know the parameters, the dynamic parameters you don't know, we call this as a PID controller, in which case PID control, where we do not know the parameters. Okay, all dynamic parameters are ignored. So we don't care about the dynamic, we don't care about the mass of the link or what is the motor torques or friction or so on and so forth. We just use, this is more like a black box control. We don't care what is inside. Okay. As opposed to this, there is a different control strategy, which is called the computed torque control or model-based control. So this is, as opposed to this, we have what is called the computed torque control. This is also called model-based control. Okay. In this case, you need to know the dynamic parameters. Okay. The dynamic parameter should be known. Only then you will be able to compute the torque or the force. So in this case, based on these parameters, based on the model, torque or force is computed. Okay. So we'll briefly go over these two control strategies, which one is a PID control or black box control, which basically does not require you to know what is the parameter. It's just like moving something and what we do in everyday life. And computer talk control is a very calculated or very precise control method, because in this case you take into consideration all the dynamic parameters of the robot. Okay, so let's take an industrial arm and we'll see how black box control or a PID control works. So normally when you have let's take a single joint. When you have a joint like this, okay, I can apply a torque. In this case, I can apply a torque or I can apply a force, right? If it's a revolute joint or a prismatic joint, we can apply a torque or a force. The output of this will be two things. It will be a displacement theta d and the rate at which the joint was moving, right? When I applied the force, what was the joint velocity and what was the joint displacement? Right? The idea is to compute the torque or the force such a way that theta d goes to the desired value, or joint velocity, you attain a joint velocity that you planned for, right? Because when we did, we had q of t as a1, a0, a1t, a2t squared, a3t cube, and we also had v of t. Right? So you can also track v of t is nothing but, this is nothing but q dot of t, and this is q theta, right? All right, so if you want to do this, what we do is we add a controller here. This is my, let's say my manipulator. Okay, we'll add a controller here. Alright, so the manipulator will generate two things, theta dot. The controller will give it a torque like this, and here you need to have a, let's do it like this. Let's do two values. You can have one, but anyway, let's do two values for now. So this will give you, let's call this as QD dot, let's call this as A and A. So here we'll take a negative feedback. This is minus, this is plus, same thing. We'll take this from here. This is minus and this is plus. So what you have here is, here we will have a value called E, which is the error, and this is E dot. Okay. Now, when you look at this, your theta A, or let's start with here, this is the trajectory generator. This could be a cubic polynomial, like that. This could be cubic or quintic polynomial. Okay. This will generate a trajectory for all the joints, let's say it's a 3 degree of freedom manipulator or 2 degree of freedom manipulator, it will generate theta 1, theta 2, theta 3, and theta 1 dot, theta 2 dot, theta 3 dot. QD or theta D is your desired trajectory, or let's say desired joint displacement. Okay, QD is your desired joint displacement, or theta A is your actual. Okay, so when you talk about E will be equal to theta D minus theta A. This is your error in the joint position. Okay, so E will be error in joint position. Similarly, here, theta D dot is your desired joint velocity, and theta A dot is the actual. So we can write E dot as error in joint velocity. So when you have this, what does the controller do? Based on these two errors that you have, the controller will generate a torque. Okay, so it will take the torque is generated torque, or I'm going to write it as a force based on whether it's a revolute or a prismatic joint. Controller will take the two values, which is E and E dot, and it will give you a torque. In this case, there is no model parameters. No model parameters are fed to the controller. The controller does not know what happens after this, how this torque is being used or anything. It does not know. All it knows is these are the two errors, and it will work to minimize the errors. Ideally, E should be 0 or E dot should be 0, right? Ideally, your E and E dot should be equal to 0, right? So it will move towards, all it does is tries to minimize the error. It does not know how you're going to use the torque that comes out of it. So in this case, we'll write it as, if you're using two parameters, we use what is known as controller gains. So let's say we have two gains. In the simplest form, we'll take two gains, which is, we'll write tau as Kp times E plus Kd times E dot. Okay? Kp is called your proportional gain, and Kd is called derivative gain. These are two values, or two controller parameter values, Kp and Kd. So Kp and Kd will decide the two gains. So if I have to draw the controller to include these two, what we'll do is, we'll write it like this. So we'll have the manipulator here, or let's call this as the robot, right? Here you have theta A dot, and we want to give it a, let's call this as a summation. This is the torque, all right? proportional gain, derivative gain, this will be minus plus, sorry, this will be okay. So what you're doing is you take theta A minus here, you'll subtract it from theta D. This is your desired. So here you get your error E. Okay. E times Kp, this will give you E times Kp here. Error times Kp. And this will be E dot. Right? So here what you're doing is you're calculating E dot as theta desired minus theta actual, right? Then you multiply this by Kd, which is your derivative gain. Okay. So this, because you have two gains here, this controller is called a PD controller, proportional derivative controller.
Professor, what is KD?
Kd is derivative gain. Derivative. Because you're derivating, right? This is E dot is nothing but okay in unit time. So it's a derivative gain. Proportional derivative control. Okay, so in this case, everything is in thetas. So this is a trajectory generator. This is happening in joint space, okay? Because here you have thetas, here you have thetas. All of this is your calculation in joint space. This is your PD controller. Let me highlight this. This part is your PD controller. All right. So this will take in theta D dot, and it will give you a torque or a force, which you then apply to the manipulator, and the manipulator will generate a displacement based on the torque. Ideally, theta A should be equal to theta D. There should be no error. It should follow smoothly. But that depends upon how you configure the two gains, Kp and Kd. Okay? This will decide how the manipulator will behave. So in this case, just without knowing the model parameters, if I can tune Kp and Kd properly, my manipulator will work perfectly. So for example, if I want to move, I have a pick and place job, I have a tool here that I want to move from here, from A to B, and I want to place it here. It will work very perfect. Okay? So these kind of controls work amazingly well, so long as you have a specified trajectory. If I change the trajectory, it's not going to work. You have to retune the gains. So, and secondly, one of the other limitations of this architecture is that this works very well when you do low velocity or slow moving applications. So in this case, the performance depends on tuning of the gains. Okay. If the gains are well tuned, then you will have a very smooth performance, but that is limited to a given trajectory. Okay. The gains have to be retuned for a different trajectory. So if I change the trajectory, I'll have to retune the gains, okay? Because once it works properly for this set of values, it might not work. If I change the loading of this, let's say the workpiece plays differently, even though I'm moving from A to B, obviously the torque needed is different, okay? So let's say I was moving wood, now I'm trying to move metal. This set of gains might not work properly. So this has to be retuned. The advantage of this is that model parameters need not be known. Okay, this works very well, this architecture works very well. For low velocity applications. Okay, so if you want to move slowly, this is a very easy way of doing this. In this case, secondly, you don't need a lot of computation. All you're doing is you're subtracting and you're multiplying by the gain, and then you're adding it, okay? So it is computationally non-intensive. That means it does not involve a lot of computations. It's very fast. All you do is, this is your sensor output, okay? It will tell you the instantaneous position. Here you have a pre-defined trajectory. You subtract it, multiply by the gain, and you add these two, that's all. So this is a very fast computational architecture. However, as you know, the disadvantages are, you cannot apply this for any trajectory. It works for a specified trajectory. Once you change the trajectory, you change the gains one side. However, it's very popular for industrial applications. Popular in industrial applications. The reason is because industrial robots keep doing the same thing over and over again. So once you set up these parameters, they'll work perfectly fine. So if you are doing a repeated job over and over again, then what you can do is, you can just configure this in such a way, and then it will stick to doing the same thing accurately. However, if you change anything, you have to retune the gains. Okay? So that is one of the major limitations. Now, in this case, if you look at this control architecture, everything is in joint space. This is done in joint space. Okay, Q. All right? If I want to convert this joint space, if I want to work, if this trajectory generator is in Cartesian space, let's say that I'm not generating QD and QD dot. My generator, trajectory generator, gives Cartesian coordinate points. So if I get X and X dot, then how will this change? What do I need to do if I'm getting, instead of Q, this is theta and theta dot, right? This is Q, this is joint space, this is joint angles, right? If I have this, which is your Cartesian space, what do I do? How would this change? What do I need to add or subtract? If I want to work not in joint space, but I have a trajectory generator, right? So this is giving me X and Y. So I have let's say that somebody gives me a trajectory generator or a trajectory. If I give you a trajectory, that's in Cartesian space. It's moving from A, which is X, Y, Z, to some point B, which is X dash, Y dash, Z dash. How can I use the same controller now?
PID.
You already have PID. I'm asking you what will change. E error. Now, what I'm asking you is the following, right? Previously, we had a trajectory in Q dot, right? So, it's understandable because when I move a joint, the joint displacement changes, right? So if we are doing independent joint control, so we have to tackle each joint separately. So if you have 3 joints, this controller will be repeated 3 times, right? For each joint, this is joint 1. This will be theta 1D, theta 1 dot, and so on. So if this generator gives me, for a 3 degree of freedom, it will give me 3 joint angles and 3 joint velocities. So I'll repeat the same controller, independent controller, 3 times for each of the joints. Now in this case, I'm not given the joint angles in trajectory. I'm given the position in 3-dimensional space, right? So how can I use the same controller? How can I apply the same controller in this case?
Can we apply forward kinematics?
Exactly. So what you do is, in this case, forward kinematics will give you this from here. Forward kinematics, F, forward kinematics will give you of theta, will give you X, right? In some places, you'll have to use inverse kinematics where you have to find X from this, theta from X. So what we'll do is, we'll adapt the same controller, but now what we'll do is, we'll add 2 modules to this, which is forward and inverse kinematics. So let me do this part, and you'll tell me what should I do for the velocity. So let's say I have over here, I have theta A, right? And I want to see, let's draw the same thing here, plus tau. Okay, so you have, this is Cartesian trajectory generator. So this will give you a Cartesian point. With inverse kinematics, you'll convert it into theta. So this function will be f is equals to, theta is equals to inverse kinematics, okay? This will do inverse kinematics here. All right, so the controller remains the same. Let me highlight the controller here. So here you have your controller.